In this demonstration, we will validate interface-level connectivity and the throughput obtained during transfer using the G51-AFibre-200G SmartNIC. The G51-AFibre-200G SmartNIC is a powerful 200 gigabits per second network interface card, engineered for next-generation data center acceleration. The images shows the hardware block diagram of G51-AFibre-200G SmartNIC card. The SmartNIC consists of Intel's Agilex 7 F-Series FPGA with dual F-tiles, delivering high-performance, low-latency compute for complex networking workloads. It offers massive I/O bandwidth with PCIe Gen4 x16 and dual-mode QSFP-DD ports supporting up to 200 gigabits per second of network throughput. The card features a comprehensive memory architecture, 8GB DDR4 for the HPS, 8GB ECC DDR4 for the programmable logic, and dual QDR4 SRAMs for ultra-low latency access. Additional storage includes 32GB eMMC and M.2 NVMe, all tightly integrated with a quad-core ARM Cortex-A53 processor, making this platform ideal for deterministic packet processing, edge acceleration, and full-stack SmartNIC development. Let us show you what the hardware looks like and how it's connected to the server to test this demonstration. The Altera Agilex 7-based FPGA G51-AFibre-200G SmartNIC, supporting Gen4 x16 PCIe finger. Single 200G QSFP-DD cage, single Gen4 x4 NVMe slot, 1G Ethernet or J45 port, SMA connectors designed for PTP applications. Its form factor consists of 254 mm x 111.15 mm, 3x4 length, full height, dual slot with active cooling PCIe card. Eject the riser cabin from the server, then insert the SmartNIC into the Gen4 x16 slot. Place the riser cabin back into the server. The SmartNIC fits perfectly inside. Close the chassis, connect the monitor to the server to execute applications, and power on the server. For this demonstration, connect the 200G loopback QSFP module to transmit the network data. For this demonstration we used BaseNIC design. The block diagram illustrates the BaseNIC FPGA design for G51-AFibre-200G. The BaseNIC FPGA shell on the G51-AFibre-200G enables a high-speed data path from PCIe Gen4 x16 to 200G Ethernet. The host sends data to and fro the card via the PCIe Gen4 x16 fingers, which interfaces to the PCIe hard IP integrated in this design. The PCIe hard IP gives out TLP packets which are then processed by the TLP adapter, which converts this into a PCIe DMA interface. The VirtIO DMA then handles the role of the DMA engine, which moves the packets to and fro the host. VirtIO DMA can be used across different distros of Linux running on the host PC. Packets then flow through a programmable packet processor for segmentation, filtering, and classification, before being forwarded to the 200G F-tile Ethernet IP and out through the QSFP-DD interface. A centralized management module oversees configuration, control, and smooth operation across the entire design. The BaseNIC design is even integrated into the 400G SmartNIC hardware to validate the 400G network data rate with certain changes. The G43-AFibre-400G with Altera's BaseNIC FPGA shell delivers ultra-high throughput using PCIe Gen4 x16 and dual 400G Ethernet ports. Host-side TLPs are received via the PCIe wrapper and passed through the TLP adapter to the VirtIO DMA engine. The data is then routed through a programmable packet processor, enabling high-performance segmentation and classification. The processed packets are forwarded to two 400G F-tile Ethernet IP blocks and transmitted via QSFP-DD cages. It also includes centralized management block oversees system configuration and coordination, ensuring stable and efficient operation. Upon system boot, the device is successfully enumerated and appears under the PCI devices list. It supports basic capabilities such as ACS, SRIOV, and VirtIO. The interfaces are bind with ViRT-IO PCI driver. With ViRT-IO net, the Ethernet interfaces are listed under IPA command. In this demonstration, we will use the IPU management tool to retrieve device statistics and configuration from the host. The tool allows users to configure the shell, view system settings, and monitor Ethernet and other module statistics. The command interface is user-friendly and easy to understand. Certain commonly used commands are listed during the demo for quick reference. The Ethernet configuration is listed using Management tool. For the G51-AFibre-200G, the Ethernet rate is displayed as 200G. In the case of the G43-Fibre-400G, the Ethernet rate is shown as 400G. The Management tool provides access to a SAF configurations and displays PF and VF mappings. It allows users to view, add, and list TCOM rules. The lookup table can be viewed, added, and deleted using the tool. In this demo, we'll walk through two test cases that validate SmartNIC functionality and data flow. The first one is the PF to PF reachability test. Here, we establish communication between two physical functions, PF0 and PF1, on the same SmartNIC. We're using a simple ping application to verify that packets can travel from one PF to the other and back. The packet flow starts from the host, enters the card through a SOFS, the onboard logic, and then returns to the host through the second PF interface. This test confirms the internal data path between PFs is functioning correctly. The second test is the PF line PF test. In this case, we use DPDK's PFIN application to generate and receive packets. Here, packets are transmitted from the host to the SmartNIC, go out over the Ethernet line, and are then received back through the card and returned to the host. This end-to-end test validates both onboard processing and physical link integrity. The packet flow begins at the host using ping application, enters the SmartNIC where it's internally routed through a SOFS logic, and then returns to the host via the second PF interface. To perform ping, execute PF0 PF1 ping script file. The script contains hardware register configuration, create data path to perform data transfer between two PFs using Management tool. Create virtual network spaces for the PFs and assign IP address to each interface and perform ping between the interface. Execute PF0 PF1 ping. In this test case, we're showcasing packet transmission using the DPDK packet gen application. Packets are generated on the host and sent through the SmartNIC, where they're processed by a SOFS logic. From there, the packets exit via the Ethernet interface and are looped back into the SmartNIC through another port. They're then processed again by a SOFS and finally received back on the host. This demonstrates the complete data path, host to SmartNIC, across the Ethernet link, and back, validating both external link functionality and onboard packet handling. For the second demo to perform throughput, execute PF0 PF1 packet gen. The script contains hardware register configuration, create data path to perform data transfer between two PFs, create virtual network spaces for the PFs and bind with VFIO PCI driver and execute packet gen application. Execute PF0 PF1 packet gen. Set the data size and forward conditions. Copy the forward conditions in packet gen application. And start data transfer from port 0. The system reliably achieves throughput exceeding 190 gigabits per second. Show packet transmission and reception statistics. The line RX, line TX parameter shows the number of packets received and transmitted. With the tool, View the host TLP statistics, PHY statistics, and DMA statistics. iWave's portfolio of SmartNICs is designed to cater to a wide spectrum of networking requirements, from mid-range to ultra-high performance data center environments. These SmartNICs are available in various configurations supporting multiple data speed options, including 200 gigabits, 400 gigabits, and even 800 gigabits Ethernet. This diverse range enables customers to choose the ideal solution based on their bandwidth demands, whether it's for enterprise applications, cloud environments, or next-generation AI workloads. The brochure for these SmartNICs are available on iWave website.